Anyways, like I was talking, guys, if you look at the units itself, you should be able to tell a story, right? 4,200 joules per kg degree Celsius versus aluminium. Versus aluminium that is only 900 joules per kg degree Celsius. First question, which one is easier to heat up, Leanne? Which one is easier to heat up based on the units itself? Which one will get hotter faster? 900, the aluminium. Good. If you think about it logically, if you put aluminium on top of a hot stove, right, versus water that is in the hot stove, like you contain it somehow, right? You'll obviously notice that if you touch the aluminium versus touching the water, you just dye your hair, by the way.
No.
Was it this brown all this while? I didn't notice until today. You sit right under the lights.
That's like.
Oh.
Okay. Yeah.
Is that ever allowed in your school? School
No,
no cares. For the gram. Okay, but anyways, if you put water and aluminium of 1 kg in the exact same pot, right, you'll notice that aluminium will be much easier to heat up compared to water. Why? Because based on the units itself, you can tell the story. For aluminium, you only need 900 joules to heat up 1 kg of aluminium by 1 degree Celsius. Whereas water, you need 4,200 joules to heat up 1 kg of water by 1 degree Celsius. Meaning to say, if I were to put numerical values, guys, let's say, for example, I supply ngam ho 10,000 joules of energy, right? What's going to happen here is that this, oh my God, have I been recording? Yeah. What's going to happen is that when you heat up the aluminium, because you're only supplying 10,000 joules, this water will only increase by like roughly 2.3 degrees Celsius if you press it in your calculator. Whereas aluminium, it would have increased by roughly around 11 degrees Celsius, right? Now, before I proceed on, are you confused with how I got this 2.3 and 11 degrees Celsius? Yes. Why are you confused? I'm supplying 10,000 joules. This one requires 4,200 joules for every kg to change it by 1 degree Celsius, right? So if you take 10,000, you divide by 4,200, it will be somewhere around 2.3, right? Right. Whereas for this 900 joules of specific capacity, I need only 10,000 joules to change it by 11 degrees Celsius. Can you see this or not? Do you guys understand how the mathematics work out or not? From here, I can definitely tell that aluminium, which has a lower specific capacity, will obviously be much easier to heat up compared to water. And if you think back about the experiment that we just did just now, right? Before we start this experiment now, what we usually do is, right, we'll actually soak our hands into water first, because when, why is it not laying? Hey, can you open the door for me, please? It should be Natalie. Right. So if you see this bucket of water here, right, which you all are going to be doing, why is it not playing? What the hell? Do we exceeded the amount of playable time? Oh my God. Yeah. Oh, is it great? See, if you see this bucket of water here, right? What the fuck is going on? Yeah, but anyways, what the hell? Wow, jam already. But yeah, anyways, what we're going to do is, right, next week when everyone is here, right, or we can do it this week as well, but I don't want to waste time of everyone that is online, right? We're going to have a bucket of water, and then the idea is that this water, which has a high specific capacity, right, we will first pour in all the kind of soap or detergent that you can see on the table there, right? So what happens is, right, when we do this, when we put in the butane gas, which we are actually pumping butane gas into it, the butane gas will actually be trapped into the bubbles of the foam of the soap and whatever. And when we scoop it up, because our hands are all covered with water already, right? When we heat up the butane gas, obviously it's going to burn for a while, but because water has a high specific capacity, it will not burn through our hand and damage our hand through any kind of fire burns, basically. So this is what we're going to be doing next week. But you guys want to do it this week? Yeah, maybe like next week when there's too many people, it'll be a bit hard to play with. Yeah, I'll play with fire. Oh, by the way, guys, for those who are going to be playing with this later on, right? The concept is you're going to scoop the thing, right? You're going to scoop it up, and then when we ignite your hand, don't go like this. You know, like you go like this, then you're going to burn the whole. You're supposed to stretch out your hand and flick it downwards. Okay, flick it downwards so that the fire doesn't the face up, basically. Okay, everyone, I'll play today. And for those who are online, sadly, you cannot join today, but I will assign you guys with some exercises. You can definitely, so many of you guys are online today. Yeah, I'm going to assign you guys with some exercises. You can definitely watch the video to check out what we're going to be playing with today. But yeah, we'll do it again next week when you guys are coming. How many of them will be here? Probably Wing Yan, Ian's, and Ivan. Yeah. Okay, let's try to do it. Wait, let me assign you guys with some homework first, because I need to prepare some of the stuff. Yeah, let's go for a past year paper here. You're supposed to do your work though. Look at this guy. Nah. Okay, yeah, you could. Let me just assign some work first, guys, so that those who are online, they have something to do. Wow, those that are here, you can play with fire today. You guys will probably, we just finished the electricity chapter, so we're going to do a little bit on the electricity exercises here. Let's do some circuits, parallel and series circuits, which I think most of you guys struggle a little bit with. Let's do some of that. Oh, I reworked it. Yeah, let's send this over. Yeah. Guys, for those who are online, please do the exercise that I've sent on the group chat, and then we'll discuss the answers in probably 20 minutes. Yeah, for those who are online, please do it right now. You can start off with the 2017 February March paper first, guys, which is supposed to be this one here. All right. Yes, please do it right now. While the rest of you guys, you can follow me. Let me get oh my god. Yeah, for those who want to watch, oh my god. For those who want to watch, I guess you could watch here. Oh my god. Probably gonna be a bad angle. Yeah. Okay. Don't tip it. Oh shit! It seems like it's gonna fall. Okay. This looks like a bad idea. Yeah, don't hit this up. Yeah, sounds like a very bad idea. Probably not here. Okay, here. Okay. All right. So the idea is simple, right? If we just inject this butane gas inside, the water is not going to hold any of the gas. So what we do is we're going to include all this soap and detergents and whatnot. Okay, coming some from some. Right. By the way, there's a bucket of water here. There's a bucket of water here, guys. All right. Yeah, let's just like hum. Probably a little more. Okay, so then after that, we're gonna stir this shit up. Stir. And you can start seeing some bubbles form here, right? And this is basically what we want to do, okay? The first thing is, guys, when you want to try this experiment, you want to soak your hands wet a little bit, because like I said, this layer of water, which has high specific capacity, is the one that's going to prevent you from getting burned, guys. So make sure you wet your whole hand first. Right. Then once you wet your hand, obviously what you can do is you can take this in and soak it in and start make some butane gas. Yeah. That's a lighter. What is that? Okay. So once you have this already, right? Common mistake with the students is, right, one time the students actually light the whole thing on fire. Before you want to do this shit, right? You want to scoop this up, push this to the side, right? And then, yeah, light me up. Hey, did I get you? Did I get you? I definitely got you, right? Yes, now who's next? Now, guys, I want to say y'all later, right? When you try the experiment, a lot of you guys will panic a little bit, which is normal, right? Make sure when you panic, you like do this, you do this, you don't like panic, and you go like this, then the fire is just gonna rise up to your face, guys. Right? You swing downwards, okay? Is someone recorded? You recorded?
I stopped.
Oh, yeah. Yeah, who's next? The boys first, for sure. Maybe show the girls that it's definitely safe. Okay, yeah. Okay, stand here.
I come back fire.
Okay, right. So I'm down your hands. Okay. So you want to soak your hands in water first, right? And then probably you don't want to scoop so much during the first part. Make sure your hands lower a bit because of your head problem. Okay, so what we're going to do next is we're going to inject the butane gas in, right, which will be trapped in bubble form. Don't scoop that much first the first time, maybe a little bit less than what I thought. Yeah, something like that. And make sure to flick down, down, not left, not right, down, flick down, flick down, flick down, flick down. Yes, excellent. Did that hurt or not? No, not at all. Because of the specific capacity. It won't be that hot, but it's going to be a little bit hot, right?
Jesus.
Now the girls. So we're going to show some girl power, okay? Right. Yeah, socks and any bracelets or whatever, please remove it first. Any watch or whatever. So, okay, make sure you click down, click down. As soon as you feel hot, you click down. Okay, I'll let you know. Wait. I heard it's soap and shampoo and everything, right? Okay, now you remove your hand, then you scoop the bubble out. Who's the fire there? You. All right. Excellent. Probably you want to scoop a little bit, not too much. Yeah, scoop. Yeah. Okay. Down. Nice. Good. All right. Does that feel good? You want to do a train with a train. But it's a bit dangerous the train, because like you hold it, then you got to pass it on, it's going to heat up a little bit. Sure. But we'll try it a few people first, okay, not probably that everyone. Okay, who's next? Let's go. Huh? Boys, I want this first. Okay, so you're a fire guy now. So your hand, wet your forearm. Okay, make sure it's evenly wet. Right. And scoop just a little bit, okay? Down. Yeah, down. Not left, not right. Down. Okay, all right. Let me do it. Let me do it.
What, chain?
Yeah, chain.
Okay.
You do me first now. Pass it.
Right here.
Yeah.
I'm gonna guess that.
You feel the heat, I think your hand burned a little bit. Yeah. But yeah, it's easier to do 2. It will be harder to do 3 and 4 is not recommended. Who's next? Let's go. Hey, wet your hands. You should have whole 4 arms better. Okay. Okay. Yeah, when the bubble comes, you scoop. Wow, so much!
Steady!
Down. Yeah, down. Down. Alright, next. Go. Take it for the Instagram. I think it'll be quite fun. Next. Let's go.
Slow.
Wet it with water, not with soap. Alright. Nah, remember, no panic, jangan panic. The hair.
Very good question.
Do it like this. Then make sure you flick down, okay? Yeah, wait, come, let me soak your hair.
No, you just help me put my hair behind my ear.
That would be definitely a good idea. Okay.
少 right?
哇，還以為你冇幫眼，你係哪個啊 ？Okay, let's put the bubble. 好啦，我哋擦乾佢。Okay. Down. Okay. Down. Nice. Okay, good. Next. Let's go. Okay, last one, then we go back to class already. Okay, you want to wet your whole arm and whole forearm with water. So that, yeah. Then you stoop down. Okay. Last one. Let's go. Do this.
Oh no!
Get away with it.
I put my hair out.
Oh my god!
Gone wrong.
Yeah, that was exactly what happened last time. So, fuck up. Who fucked up?
Smell.
But you can definitely smell some hairs now. Barbecue that.
You put it on hair?
来到有人。哇，那个味道是啊，哇错。Oh my god.
Yeah, but yeah, that concludes the whole experiment. The next week when we come back around, we'll play with different something else. We'll play with convectional current, or we could even play the coconut experiment. Alright, fun. Okay, yeah, everyone.
Put your hair.
Okay, so my hello.
Yeah.
Okay, yeah. Okay, boys, I want you to help me do a favor. Okay, you cut 3, and then you wipe until the whole tissue is gone, then you throw it away and do it again. Yeah, clean that right up, boys. Yeah. Goodness. Burn hair smell in the air. I can just throw it in, guys. Guys, let's throw in this product. Okay. And that's how we. Yeah. Next week we'll play something else. Yeah, and you pay off. Yeah, quite a lot of burn hair on the ground as well.
Thank you.
I think the last one I didn't wet my hand enough. I got a little bit dirty. A bit red already. Yeah, but that's essentially what it is. Haha. Did everyone get to witness Leanne burn her hair a little bit? Okay, everyone, sit back down. Let's continue back class as per normal. Oh my god, Wing actually left.
Oh yeah, crispy.
Crispy 啊，炸鸡头发。But don't worry, for 1 year, right? My student, he burned all his eyebrow. You know why? Because you know, like a bucket that I keep saying, like push it away. We were like lighting fire under it, and then boom! Wow, his whole eyebrow burned, man. I was so scared. I'm like, shit, am I gonna get sued? Because you know, like but it was okay like then. Yeah. It's okay 啊，你有那么多头发，不用怕，你还是那么美的。
And the eyebrow won't be like, you know.
I tell you, the guy's eyebrow is like burnt, then it's like crispy burnt eyebrow here. Oh, that was a good stuff, man, I tell you. But yeah, maybe next week we can try a different experiment. Why?
For me neither.
Why?
Yeah.
Yeah. But I think next week we're going to proceed on with the new chapter, though. Are you sure you guys want to come?
Yeah.
Yeah. GG. After. Okay, so that concludes the experiment. Let's go back into the exercises. Guys, these are all in your booklet, guys. Oh, by the way, have you got your book yet?
No.
Go outside, take 2. Who else hasn't gotten it yet? I think Ivan is right. Can you guys pass it to him later before you guys go? Pass it to him. No, take the one with the exercise and the notes one. One that says EX, yeah, then that one that says notes. Yeah, that's yours. Okay, guys, if you flip to the year 2017 for 4.3, guys, I think for the benefit of the students that are online, let's go through this question straight away first. And after that, oh my God, can you pass me my mouse? Yeah, then after that, we'll give time for everyone to do the next one together. All right. Hey, faster, like flip your.
Huh?
Hey, send me the video. Hey, whatever videos you guys have later, send it to me or tag me on Instagram, okay? Yeah. What happened? Is it the first one?
Yeah. Okay. Oh wait.
Oh my God, you didn't get it, huh?
I did.
Just now I did it to Mary's, right? Mary's bunch, right? And she's like, she was so scared. I laughed so hard. All right, guys. Yeah, let's go through this page together, guys. For those who got your booklet, it's 4.3. Find 4.3 first. Then after that, it should be the February-March 2017 paper. Yeah. It's not. Yeah, it's not. Okay, never mind. For those who, oh my God, that means to say I did not send this out to everyone. Oh no, I did. It's here. Okay, everyone pay attention. Let's go through these questions together real quick. For those who are here, just pay attention to the screen, guys. Since you guys didn't attempt it yet. Okay, so I sent it to the group already. For those who want to do it later, you can go back home to do it. Let's look at the first question together, guys. If you look at the question here, the diagram represents 4 copper wires. Which wire has the greatest resistance? Now, if you pay attention to all these things here, right, what's the formula that dictates the resistance of a wire again? What's the formula? Length over area, very good. R is supposed to be length over area, right? If it's length over area, it means to say that the resistance and length are directly proportional, meaning to say the longer the wire, the higher the resistance it is, whereas the resistance and area of a wire is inversely proportional, guys. Inversely proportional meaning to say the bigger the cross-sectional area of your wire is going to have lower resistance, guys. So if I want to have the greatest resistance, obviously I should have something that has the highest length and the smallest area. Looking at the highest length, obviously it's either this or this, or meaning to say these two are out already. And looking at the area, I want the area to be small, right? So looking at here, obviously C would have been the answer for this question here, guys. Always remember your resistance wire is going to be dependent on length and area, guys. All right. Everyone's still looking at their hands and hair. Maybe there's still some burnt hair on your head, but I guess it's fine. Yours is like completely fine already. So let's go to the next part here. Hey, everyone, pay attention, please, everyone. So the next part here is basically talking about diodes, right? This next question here: 4 circuits are set up. In which circuit does the ammeter show the greatest reading? In order for it to have the greatest reading, especially as an ammeter, we have to follow back the Ohm's law formula, right? Which is V equals to IR. I would have been equals to V over R, right? I should have been V over R, meaning to say, if I want the current to be high, I need the voltage to be high and the resistance to be low, right? Looking at this situation here, first and foremost, I noticed that there are diodes here. What do these diodes do again? Yes, very good. It allows current to flow in one specific direction. I mean to say, if this is the positive side, the current can flow here, the current could flow here. The current could flow here, but it will be stopped here, guys. It cannot flow through because this is known as reverse bias, right? Reverse bias, the resistance here will be too high. It does not allow current to flow through at all. So obviously here I can see that these are parallel circuits. This is series circuit. This one totally don't allow current to flow at all. So this will be 0. This one will be yet again another series circuit again. Now, based on the information here, without any further calculation, which one do you think will have the highest current based on A, B, or donkey? Donkey. Why? Is it because that this one has the lowest resistance? Now, this is a common mistake with the students, guys. A lot of you guys have this misconception as well, guys. Although true enough, in a series circuit, this one would have the lowest resistance because obviously 2 is lower than 3 lah. But if you do the calculation now for the parallel circuit here, how do you calculate the resistance for a parallel circuit again now? 1 over RT, very good, is equals to 1 over R1 plus 1 over R2, right? If you press this in the calculator, it will be 1 over 2 plus with 1 over 3, right? Right, everyone remember this, 1 over 2 plus 1 over 3, which will give you 3 over 6 plus 2 over 6, right? Which is going to give you 5 over 6. And this is not the final answer, guys. Always remember that this is equivalent to this only. I need to flip it the other way around, meaning to say RT would have been equals to 6 over 5, which in this case here will be 1.2. Can you see the difference here? This circuit only has 1.2, even though there are 2 resistors, because anytime you put any resistors in parallel, they will actually have more lower effective resistance, guys. Very common mistake with the students. A lot of you guys may have had the same problem as well. Always remember that parallel circuits will have lower resistance because of the calculation. Okay, everyone? Right, then moving on to this next part here. The diagram shows a electrical circuit. The light falling on the light-dependent resistor increases in brightness, guys. What happens to the resistance of the light-dependent resistor, the current in the fixed resistor, and the voltage reading here? Now, first question, if we want to dissect this question here, guys, how does a light-dependent resistor work again? Natalie, how does a light-dependent resistor work in terms of its brightness? What will happen to the resistance? Excellent. Light high, resistance low. Guys, same concept for thermistors as well. High light, low resistance, low light, high resistance. For thermistors, high temperature, low resistance, low temperature, high resistance. Guys, always remember they are opposite, right, for light dependent resistor here. So if the resistance drops here, what is the next thing that is going to happen to this circuit if the resistance here drops? Yeah. What happened? What's going to happen if the resistance drop in terms of this circuit here? What could this drop in resistance cause in this circuit here? What is it? Decrease in current, is it? Decrease or increase? Think about it. When your resistance is low, will your current increase or decrease? Your head increase. Increase. Why? The formula is R is equals to V over I. You can see that these are directly proportional and this is inversely proportional. This is according to your Ohm's law formula. So if you have high resistance, obviously the current drop. Sorry, when you have low resistance here, obviously the current increases. All right. So more current is able to flow through this circuit here. So the first question is, what happens to the light dependent resistor when the light intensity increases? Obviously it's going to decrease now, right? And current in the fixed resistor, they don't give you an option, it's only increase, right? And finally, what happens to this voltmeter here, guys? If today the resistance here drops, will the voltmeter here increase or decrease? And why? Decrease or increase? Why? Why? No, it is not. Mishan, tell me why. Increase or decrease? Wait, yes, up or down? Faster. Why? Okay, let's draw this situation up here, guys. Let me show you how this whole thing works. Oh God. Let me connect to my iPad first. Give me a minute. Oh God. Suddenly I feel really hot. I just feel hot. It's the fireman and the heart pumping. So basically, just now if we redraw the circuit here, and there's basically like a battery, then this thing is connected to a light dependent resistor, and then there's a fixed resistor here that is connected to a voltmeter, and then the circuit completes now, right? I already identified that the light intensity increase, which will lead to resistance drops, which will lead to increase in current, right? Now today, if the resistance here drops, guys, what's going to happen is the resistance here will become relatively higher, right? Guys, if you recall back the series circuit formula, guys, I always say series voltage is the piece of cake, right? Remember the word SVC and all, guys. For those who were here, probably you don't know what I'm talking about, but series voltage is a piece of cake. Basically states that the larger resistor is always supposed to consume the larger piece of cake. In series, voltage is the piece of cake, meaning to say, today, if the resistance drops here, the voltage here is going to increase because it is relatively higher already. For example, let's say just now here was 10 ohm and here is 10 ohm. Okay, let's just say for ease of calculation, here is 20 volts. Right. In this scenario, before the light intensity increased, there was supposed to be there's supposed to be 10 volts here, and then there's supposed to be 10 volts here, right? Right now, when the light dependent resistor hits, right, the light dependent resistor hits and the resistance drops, let's just say right now this thing here drops to, well, for ease of calculation, let's say it drops to 5 ohms. Hold on, let me change a different color. Let's say it drops into 5 ohms, guys, and this thing here will still be 10 ohm, guys. Can you see the distribution of voltage right now? Right now, this 20 volts will be separated into 15 parts, guys. 20 volts will be separated into 15 parts, meaning to say for each 1 ohm of resistance, we're supposed to get 1.3 volts. You're supposed to get somewhere around 1.3 volts, guys. And from here, we can clearly see that right now, instead of getting 10 volts, this guy is going to get 13 volts, and this guy is going to get the remainder of the volts, which is 7 volts here. Can you see it not? Originally from here to here, originally from here to here. Always remember, guys, in series, voltage is the piece of cake. Whichever one has the higher resistor will have the higher voltage drawn from the battery. But for parallel, it will be a totally opposite scenario, guys. For parallel PIC, right? Parallel PIC means to say current is the piece of cake, right? Meaning to say voltage will be the same. For example, if let's say I have a volt here, then here is one resistor, here is another resistor, and here is another resistor. It doesn't matter if it's 5, 3, 2, or 1 ohms, guys. As long as they are parallel to each other, if let's say this is 10 volts, this guy will get 10 volts, this guy will get 10 volts, and this guy will get 10 volts as well. Very important, guys. You should always remember the concept. SVC, series voltage is the piece of cake. PIC, current is the piece of cake. So meaning to say, obviously, if let's say for ease of calculation, let's say there's 6 amperes flowing here, guys. What's going to happen is it will be the least amount of current flowing here because the resistance is highest, right? So let's just say 1 ampere. Then there's going to be a little bit more here. Let's say 2 amperes, and obviously there's going to be the most here, which is, let's just say 3 amperes. PIC, parallel current, is the piece of cake. The current is the one that splits between all the other resistors. Remember this, is like super important for the electricity chapter. If you don't recall this, it's very hard for you to tackle all the questions, because in your IGCSEs, they will not only ask you for parallel and series circuit, they'll ask you like diodes, like dependent resistors, and some are in parallel, some are in series, and so on and so on and so on. The basic concept must be understood first, guys. All right, everyone. Anyone's got any questions for this part here, especially for the series and voltage part? Sorry, series and parallel part. A lot of you guys usually get a bit confused about this part here. No one's got any questions? Excellent. Then I'm sending this document to my iPad, and let's continue from here. Oh God, no! What? Oh, I'll just send it again. Okay, so Look at this question here back again. Like I mentioned, guys, you're supposed to understand that if the resistance here drops, that means to say the resistance here will be relatively higher, and when resistance is relatively higher, your voltage is supposed to be higher as well. Understand? Next, moving on to the next part here. The diagram shows two linked circuits to control when a bell is switched on. The conditions are altered, and only one pair of the condition causes the bell to ring. Which pair causes the bell to ring? Bright light and high temperature. Bright light means to say resistance here drops. High temperature means to say the resistance here drops. If the resistance drops, it means to say more current is flowing. By the way, what's this thing now? Excellent. It is called a relay. You have saved someone again. This is a relay, guys, which is essentially what we talked about last week, guys. Relays are basically the ones that work with the small current controlling the large current, guys. So in this scenario here, this would have been the small current, and this would have been the larger current. You guys see it or not? And obviously, in this question here, A is going to be the answer because we want the current to flow here. When the current flows here, this will become magnetized and will attract this thing here, and this thing will turn on. You got what I mean? Okay? Yeah. Then this next part here is a little bit tricky, guys. For those who are online, anyone did this question already, guys? Any of you guys done this question for those who are online? Are you guys doing this question? If not, then let's do it all together, guys. Anyone? 5, 4, 3, 2, 1. Okay, let's do this question together, guys. Yeah, let's do the first part first, guys. Everyone, tell me how much the current is. You have 2 minutes. Shit. Thank you. Okay, 2 minutes, guys. Tell me what the answer is for this part here. You want to see? Yeah, the icon is crazy. You might want to write it down for those who are not so good. Definitely, it will help, guys. Sliding contact is like basically a variable resistor. If you slide it using more resistance wire, it will be higher resistance and thus lower current. If you slide it towards A, then we'll be using less of the resistance wire, means lower resistance and more current. But the first part is not relevant with the sliding contact. Is it 1.5? Hey, what the hell? 我跟你讲，你等一下你跟我拿那本书然后你回去做I've recorded everything of mine. I think you and Ian wanted it, right? Was it you or was it Ian? Okay, yeah, guys, what's the answer? Vicky, what formula should we use? Equals to what information do you have? I over V. I don't know. I over V or what? It's IV lah or VI lah. Hello, power formula and this one. Right now, power equals to VI, am I right? How do I know to use this formula? Because I'm given this information, right? This is clearly going to be power and this is clearly going to be voltage. And if they're asking me to find current, these three things fit into this formula. Right, so from here, it's just a matter of algebra law, right? So I would have been equals to P over VL, which in this case here will be 9 divided by 6, which is 1.5. And yet again, you are correct. Okay, it's supposed to be 1.5 amperes. Guys, look at the next part of this question. It said that the resistance of the lamp at normal brightness. How do I find the resistance of this lamp here at normal brightness given these type of information? What formula should I use, guys? Sorry? I equals to? Oh, yeah, correct. Yeah. You're supposed to use the R equals to V over I formula. You could alternatively use the P equals to I square R formula, or you could use the alternatively V square over R formula. Guys, how many of you guys, do you guys know how to get this formula, by the way? Except for Tristan here. Guys, how do I get these formulas again? Do you remember? It's derived from the Ohm's law formula now, guys. You know, like how I always tell you that P is equals to VI for the electricity formula, right? P is equals to VI, this is the general formula that we all remember, right? And we also remember Ohm's law formula, which is V equals to IR, right? Today, if I substitute this V into here, what will happen is it will become P equals to IR times with your I, right? Which gives you the final formula of I square R. You can use this formula if you're given the power component, you're given the current component, or you're looking for the resistance component, right? This is one way to do it. Alternatively, if you don't want to use this, you could use the P equals to V square over R formula, which is yet again just a rearrangement of the Ohm's law formula, guys. From here, you could substitute this into here, and what you're going to end up with is you're going to get P equals to V over R, right? Which will give you the ultimate formula of V square over R, guys. Now, guys, it is very, very important that you remember all three of these formulas, because depending on different situations, they will give you different components, and you're supposed to use different formulas. Yeah. Right. So from here, look at this scenario. You can use either one now, right? But since you have V, you have I, you have R already, either one is going to be acceptable. You could either use the R equals to V over I formula. You can use the R equals to P over I square, but I'm sure no one does that. You could also use the R equals to V square over P formula, which I'm sure no one uses as well. Yeah, depending on situation, guys, you can use either one. In this situation here, obviously V over I is the easiest one, which is going to be 6 divided by 1.5, and ultimately we'll know that it's going to be 4 ohms. I know for a fact that this light bulb here will be working at 4 ohms resistance. Okay, last part. I want you guys to try to do this on your own. Oh, cut this. So we cut this. Oh. Oh, wow, drop everything else available. Let me put back all the relevant information in, and then you guys can try to do the last part here. This thing was going to be 4 ohms because the current here flowing would have been 1.5 amperes. And then this part here. Everyone start attempting this part here. The more important part is going to be this one here, guys. It's going to be a 3-mark question, I think. Try to do this. I'm going to give you guys probably 5 minutes to figure it out. Oh, and you need the power. What was the power again? What was the power? Power was 9 watts. It was 9 watts. P equals to VI, and this was 6 volts. Yeah. Okay. These are all the relevant information you need. Try to do the calculation here. It's 3 marks, guys, for B2. 5 minutes before I review how to do this question. Sorry? This sliding contact, right, is basically allowing how much current to flow through the resistance wire. Can you see like the current is flowing from the left to the right now, right? If let's say my sliding contact is closer towards A, the current will bypass the whole AB and go through just the normal wire. Can you see? But if I slide it towards the right, towards B, you see the current has to pass through A, then B only go through the sliding contact. So it means to say the current has to flow through a lot of resistance on the wire, which will make it lower current. For those who are having a hard time imagining this, guys, this sliding contact is basically dictating how much current is flowing in the wire. Right, so basically, if let's say my sliding contact is here, right, the current that flows through will be like this long. It can bypass the whole resistance wire, meaning to say the resistance will be low and my current will be relatively higher. But if I slide it towards here, guys, so what happens is the current will have to flow through here to here to here to here to here, right? Which means to say the resistance will be damn high and thus the current will be relatively lower. Can you see how it's going to flow, right? But yeah, try to do some calculation. Guys, don't stare at it. Look at all the information. Try to write it down. Try to formulate a formula and try to make sense of your formula. That is usually the better way to do it. And stop falling asleep. Oh my God, your eyes are so red. What time do you sleep last night? Oh. By the way, the final answer is supposed to be 0.8 meters. for those who have calculated it. Let's see how many of you guys can get it right with a proper explanation. Mr. Gilbert here is struggling too. Let's see, our most prominent student first. Now, say it. Oh, you got it, ah?
No, I just very.
How do you get this?
Because the box is. Yeah, it's.
I know. That's correct.
Correct.
Yeah, that's correct. Very good. Marcus here has found the correct answer already. B2. Very good logical guidance. Oh, how do you get 405?
Oh, is the one that is 501.
How do you get the 4? This 4 ohm here from the light bulb. How come the light bulb? Why are you talking about light bulb? Looking for a wire. Huh? Yeah, but how come? I mean, there's a lot of methods to approach this question, but how do you get 405? Where do your 4 come from? It's definitely not from the light bulb. It has something to do with light bulb for sure. 1 divided by 5 times 4. How do you get the 1 divided by 5? What the fuck? No, Leanne, that's not the way to do it. I'm going to go 1 divided by 5 times 3 or 4.
I still got answer.
It's wrong. And the resistance of the light bulb is given. Yeah, all these are information basically prior to this question. Let's test Mr. Gilbert here. You want a hint or not? Pass. If you're ready. Okay, Vicky, I think you're almost close. Let's see your thing. How do you get this 6? This or the
Yeah, you distract me.
very close.
Cannot already.
You say yeah, you're supposed to use ratio. You figured it out already, is it? You could use ratio to do it. You could use calculation to do it. There are 1,001 ways to do this question. That's why I like electricity questions the most. Yeah. Okay, guys, time constraint up. Let's go for the question. Guys, the key word here, guys, there's actually a few ways you could solve this question, but for me, I like to do calculation, right? If I analyze this whole diagram, pay attention, right? If I analyze this whole diagram here, right? This here starts off with 12 volts, right? This battery already consumes 6 volts. So how much can the wire get?
So minus 6 lah. Then that's how I got the 6.
Okay, good. So this wire, in order for it to work normally, must be 6 volts, right? Because it can't work any other way, right? If this thing here is 6 volts, and I know for a fact that current flows in a series the same, can I say that this thing here is going to be 1.5 amperes already or not? Right. And if it is 1.5 amperes, it means to say in order for this wire to be 6 volts, according to my resistance formula is V over I, right? Which is 6 divided by 1.5. That's why I say you were very close. I think you did this right. You found out that in order for this light bulb to work at a normal brightness, this wire must be only 4 ohms. But the question states that this wire is 1 meter long and 5.0 ohms, right? Meaning to say, if I identify that I want the wire to be 4 ohms, and I know for a fact that 5 ohms is equivalent to 1 meter, then how much length should the resistance be? Which you could play in ratio, which is 0.8 meters, right? But I see the Maxim, there was actually a very complicated calculation for this. But it's always better you identify all the information you have and slowly work your way backwards towards it. It will be much easier. Anyone else did a different method? What was your method again?
Ratio.
How do you found out this to be 4 ohm also, is it?
I just assume 4 ohm.
How did you find? You assume one that is wrong.
I thought when you said the lamp there requires 4 ohm to be at normal brightness, so
Yeah.
4 to 5, then yeah.
Shani, what are you watching?
Sorry.
Yeah, sorry. So you were looking at this 5 and 4 only, is it? Or you were looking at this 4 ohm and you identify that here also is 4?
Yeah, because for normal brightness it's 4 ohm. So
no, well, you were lucky lah. They was lucky when they said normal brightness to be 4 ohm. They're talking about this normal brightness must be 4 ohm,
yeah, that's right. For it to be normal brightness, right? You need to think how do you get 0.4 ohm. So you just 1 divided by 5. Then you get 0.2 is 1 ohm. Then you multiply by 4. Then you just get 4 ohm.
But you must identify that here is 4 ohm first. You must identify that it's 4 ohm first. Okay. So if you were to do the calculation, you're supposed to do something like the resistance wire. Resistance wire should be V over I, which is going to be 6 over 1.5, which gives you 4 ohm as well. And then next you're supposed to say that if 1 meter represents 5 ohms, then obviously 0.8 meters represents 4 ohm. There's something to do. You're supposed to do this kind of calculation, guys. Or alternatively, you could also add the 12 volts minus 6 volts equals to 6 volts. This 6 volts is corresponding to this one here first, guys. Right. 12 minus 6, then after that 6 divided by 1.5, then after that it's just a matter of ratio already, and you'll be able to find answer. Okay, everyone. Hey, one more question before we make a move away. How? Anyone wants to copy this down, by the way? Hold on. Anyone wants to copy this down? I think you guys should be able to solve this by now. Okay. One last question before we end the day. Let me see. Good. These kind of questions. I like. Hey guys, if you're talking about electricity, most likely they will give you this graph, guys. Looking at this graph here, anyone except for Tristan here can tell me, will this thing be increasing resistance or decreasing resistance? And why? Mishan? Will it be increasing resistance or decreasing resistance, and why? I want to consider bringing your glasses next time. Decreasing, why? R equals to I equals to V over R. Okay. I increase, R decrease. So your statement is R decreases in this graph here.
Yeah.
Anyone else got another reasoning? Marcus?
R increase.
What the? What the fuck? Why am I reading that? What the? Why did you trade? Oh, welcome back, everyone. Can you press the power button for me a bit? Everyone is still here, right, guys? Oh. Okay, guys, pay attention before we end the day, guys. The answer is the resistance is increasing. But why? Guys, this kind of questions will always come up in your exam guys. You have to know how to read this kind of graph. Some of you said that the current is increasing, and you know that current and resistance is inversely proportional, and then you say that resistance is dropping off. While it is true that your current is indeed increasing, did you guys notice that the voltage is also increasing over time? So it's not a matter of which one is increasing, it's a matter of which one increases more. If you look at these kind of graphs here, I think I mentioned this in class before as well, guys. Look at this graph. If it is tilting towards the V side, it means to say that the voltage is increasing more than your current. For every jump in voltage, the voltage increases more than your current, guys. The voltage increases more than your current because this graph here is going towards the V side. Can you see that? Meaning to say, right, if we do the formula, it's not supposed to be the I equals to V over R. It should be the R equals to V over I. And from here, if I know that voltage increases more than my current, both of them are increasing, but voltage is increasing more than your current, indicating that your resistance is increasing. Alternatively, in your graph question, guys, they always do this. Sometimes they will give you a curving down one, sometimes they'll give you a curving up one. If it is curving up like this here, the green color line, it means to say that the current is increasing more than your voltage. Then that situation here, the resistance will be dropping. Sometimes they'll even flip the other way around. They'll say that this one here is voltage and this one here is current instead. Based on wherever it's tilting towards, you have to understand which one has higher or lower resistance. You guys get what I mean, guys? Very important. This graph always comes out in your IGCSEs. So, then after that, the following questions will be as such. State what happens to the resistance here. If I look at the resistance from 0 to 1 now, which is essentially this line here, it is essentially a constant gradient, right? Constant gradient means to say it should have a constant what? Yeah, constant resistance right? And from here, you can see that the gradient is tilting towards the V side, meaning to say that the resistance is increasing. 明白吗，大家? Very important, guys. This graph always comes out, and you better be careful with the axis. Sometimes it will be I versus V, sometimes it will be V versus I. So you see which one is tilting towards, guys. Okay? Yeah, I'll end class here, guys. If you have any questions, you can always stay back. If not, I'll see you guys next week. Next week, we're going to proceed on to the new chapter already, which is the final chapter of radiation. Then after radiation, we're going to like probably do 2 to 3 weeks of exercises. Then after that, we're going to go for the full recap of all the chapters already. We'll be arranging for intensive classes. Yeah, then after that, it'll be most likely going to be exams soon already. Yes, like I mentioned, now it's already the end of May already. Oh, and I think next week there's no class, it's the 5th week. Wait, did I have class on the 2nd May? Wait, let me check. If I did not have, I did.
No wedding function.
Huh? Was it a wedding function? Oh, if it's a wedding function, then I'll have to come. Wait, let me check. 2nd of May. Okay, I did. Oh, I did it. Yeah, that's gonna be class. Yeah, that's gonna be class, guys. Yeah, it was a wedding function. Yeah, I remember it was right. Last next week, we're going to proceed on with the radiation chapter, guys. All right. Yeah, that'll be it for today. Yeah, let's go for some experiments as well for the memes. Yeah. Recording.